Hello students, welcome back to Algebra 2, Chapter 6, Lesson 6, Solving Exponential and Logarithmic Equations. So we're going to start off with something called the property of equality of exponential equations. That's a really fancy way of saying something really easy. One second. So the property of equality of exponential equations goes like this. If I have some base, so let's just say the number 6. 6 to the x power is equal to 6 to the 5th power. Basically, if the bases are the same, the exponents have to be the same. So if I have 6 to the x equals 6 to the 5th, then x must equal 5. If I had 113 to the x plus 3 power is equal to 113 to the 27th power, then I could turn that into x plus 3 must equal 27, and then I would subtract 3 on both sides and get x equals 24. So basically, if I've got an equation and the base on both sides are identical, then the exponents must be equal. So now in order to solve this equation does not have equal bases, but hopefully you can see here that they can be turned into the same base. So I know that 100 is 10 to the 2nd power. So I would just change that 100 to 10 to the 2nd power to the x power is equal to, now I know that 1/10 is 10 to the negative 1 power, and that is to the x minus 3. Now, using the power rule that we learned in Algebra 1, let me leave a little note over here on what the power rule is. Quick example, if I have x to the 2nd to the 3rd power, that equals x to the 6th power. So I multiply the exponents in this situation. So this would turn into 10 to the 2x is equal to 10 to the distribute the negative 1, negative 1x plus 3. I can solve further. Now that I have them both identical bases, I can say 2x is equal to negative x plus 3. I'll add x to both sides, and I'll get 3x equals 3, divide by 3, x is 1. Moving on, here's another one. Hang on just a second. So for our next example, we'll get this seemingly simple problem. 2 to the x power is equal to 7. Now, we could try that same technique. However, this one's a little more complicated because I don't know 2 to what power is equal to 7. So that technique becomes cumbersome. So what I want to do is remember that if I have a to the b power is equal to c, that is the same thing as log base a c is equal to b. So I can rewrite this in logarithmic form, which would give me the equation log base 2 7 is equal to x. Now that I have that, I can rewrite this using change of base. So that would be, I'm going to use natural logs. Natural log 7 divided by natural log 2 is equal to x. And then I can just use my calculator to finish that off. ln 7 divided by ln 2 is equal to 2.807. Okay, so for our next equation, this one's the same type of problem, just a little bit more complex. So we're going to use the same technique, but first I want to kind of clean it up and get rid of these extra constants. So let's go ahead and add 7, and we'll get 4e to the negative 0.3x is equal to 20. And then let's divide by 4 on both sides. We get e to the negative 0.3x is equal to 5. And now using that same rule, I can say log base e 5 is equal to negative 0.3x. Now you should have a red flag going off right here. You have log e, and we know that log e is natural log, so that'll change to ln 5 equals negative 0.3x. And our calculators actually know how to do natural log. So just off to the side here, I'm just going to say ln 5 is equal to 1.609 equals negative 0.3x. And then we'll just divide both sides by negative 0.3. And I'll get 1.609 divided by negative 0.3. That is equal to negative 5.63. Negative 5.363. X equals negative 5.363. Now, the property of equality for logarithmic equations is very similar to the property of equality for exponential equations. And that goes like this. If I have a log with some base like 5, x, and that equals a log with a similar base, an identical base, 5, 7, basically both sides are the same except there's an x and a 7. So if they're both identical except for these two pieces, then those two pieces must be equal. So in this case, I've got natural log 4x minus 7 is equal to natural log x plus 5. All I have to do is say, well then these two pieces must be equal. So 4x minus 7 must equal x plus 5. We'll just subtract x on both sides and get 3x minus 7 equals 5. Then we'll add 7 to both sides. We'll get 3x equals 12. Dividing by 3 gives us x equals 4. Now, one thing that we do want to double check though is anytime that we're dealing with equations with logs in them, there is a possibility for an extraneous solution. And if you remember that from Algebra 1, an extraneous solution means we did everything right, but the answer is still not possible. That might happen sometimes in log equations. So I'm just going to plug this in. ln 4 times 4 minus 7 is equal to ln 4 plus 5. So I get the natural log of 16 minus 7, which turns into the natural log of 9. This is the natural log. Oh, there's my mistake. I said 4x plus 3. It's 4x plus 5. X plus 5. 4 plus 5. So I get natural log 9 equals natural log 9. And just to make sure that it works, I'm just going to type in natural log 9 to make sure it's a defined value. Yes, it is. So that means 4 is the correct answer. Now, in this case, looking at this one, I don't have the same situation. So what I'm going to do is rewrite this as an exponential. 2 to the third power equals 5x minus 17. And then I can just solve this like we're in Algebra 1. 2 to the third power is 8 equals 5x minus 17. We'll add 17 to both sides, and we'll get 5x is equal to 25. We'll divide by both sides. We'll get x is equal to 5. Now, doing a check for an extraneous solution, I get log base 2, 5 times 5 minus 17 equals 3. So log base 2, 25 minus 17. Log base 2, 8 equals 3. And then just using a calculator to check, I'm going to use change of base to rewrite this as ln8 divided by ln2 is equal to, if I did that correctly, the answer should be 3. So let's just run a quick check. Natural log 8 divided by natural log 2 is equal to 3. Okay, so this one works. We can move on. Okay, so this one gets a little bit more interesting. I've got two common logs being added together. And hopefully you remember from last lesson that this is the product rule. Log 2x plus log x minus 5, I can condense these two into log 2x times x minus 5 equals 2. I'll go ahead and use the distributive property here to get 2x squared minus 5, just kidding, 10x equals 2. Now I want to remind myself here that this has a base of 10, so I'm just going to rewrite this as an exponential equation, so it'll be 10 to the second power equals 2x squared minus 10. 10 to the second power equals 2x squared minus 10x. Now, we should immediately think, oh, this is a quadratic equation. So I'm going to simplify that to be 100, 2x squared minus 10x. And then I can subtract 100 on both sides. And I get 0 equals 2x squared minus 10x minus 100. And then you are free to solve this in whatever way you see fit. You could do it by graphing. You could do it with the quadratic formula. You could do it by factoring if you like. First thing I'm going to see is that I can factor out a 2. So I'm just going to divide both sides by 2. Won't always work like that, but in this case it does. X squared minus 5x minus 50. Okay, and so now what I would do is use the quadratic formula here. A is 1, B is negative 5, C is negative 50. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a turns into x is equal to positive 5 plus or minus the square root of negative 5 squared minus 4 times 1 times negative 50 over 2 times 1. Okay, simplifying the discriminant here, I would get 25, and then I've got negative 4 times negative 50, that's going to turn into positive 200. That's inside a square root, so I get the square root of 225, which hopefully you know, but if you don't, we can use a calculator. Square root of 225, 15. So I get 5 plus or minus 15 over 2. That's going to split into 2, 1 for each sign. So I'm going to get 5 plus 15 over 2 and 5 minus 15 over 2. So that's 20 over 2, which reduces to 10. And 5 minus 15 is negative 10 over 2, which is negative 5. These are my two solutions. So let's go ahead and double check to make sure that 10 and negative 5 work. So I'm going to go back up here to my original equation, and I want to test 10 and negative 5. So common log of 2 times 10 plus common log 10 minus 5 equals 2. So that's going to be common log 20 plus common log 5. that should equal 2. So let's go ahead and just give that a try. I've got, in mine I have to type in log 10, 20, plus log 10, 5 is equal to 2. Okay, that one works out. Let's try that again with negative 5. Log 2 times negative 5 plus log negative 5 minus 5 equals 2. So this one I'm going to get log negative 10 plus log negative 10. Let's try that out. Log 10 negative 10 plus log 10 negative 10. And again, I'm typing in log 10 because that's the way my program does it. Most calculators would just call that common log equals. Okay, mine's not working. I'm going to switch over to Desmos for a moment just so you can see what happens here on an actual calculator. So if I type in common log negative 10, I get undefined. And the reason for that is that means 10 to the what power equals negative 10. And hopefully you remember that no matter what happens, 10 to no power will ever be negative. That's why we get undefined here. So in this case, negative 5 is an extraneous solution. So that means our answer is only positive 10. So I can put right here, my answer is x is equal to 10.